Hi, welcome to the 8th session on infinite series. Today the main topic is what I said, a beautiful result. Suppose I have an infinite series summation an, assume it's absolutely convergent, that means summation mod an is convergent. Now you permute a1, a2, etc. okay, in any fashion. For example, my first term, call it b1, that may be a100, and b2 may be a7, and b3 may be a to the power a to 20,000, and b may 4 maybe a 19, and so on. You just do a bijection of these things. Okay, you completely rearrange the new series summation bn is called a rearranged series. Now we want to prove something interesting. What we want to prove? Summation bn is convergent, number one. Number two, what is the sum? The sum is the original sum, namely summation of an. Now you should compare this with our standard alternating series. We know it is conditionally convergent. That means it is convergent but not absolutely convergent. There what did we see? We said we can rearrange the terms. Therefore, if the original sum of the series summation minus 1 to the power n minus 1 upon n is s, which is non-zero, then after rearrangement I can make the sum to be half of that, half s. Right? In fact, I can even do something more. That's what Riemann says. I can even find a rearrangement so that minus 1 to the power n minus 1 by n after rearrangement diverges. It could diverge to plus infinity, or it could also diverge to minus infinity, or it would converge to any specified real number. Do you understand this? So contrast that with this. If I have an absolutely convergent series, I don't have to worry about the order in which I'm going to sum. In any fashion I can sum, it will be convergent, it will converge to the original sum. Now do you understand why I said analysts love absolutely convergent series? Okay, that is the reason. And it's easier to estimate because summation mod an, it's a positive thing. You have the usual comparison test, geometric series, and root test, and ratio test, and so on. So life is much easier. That is the reason. Okay, right. Now let us get started. Let us give a proof of the result. As usual, you have the series. The title is Infinite Series 8, delivered on 5th February. The subtitle is Rearrangement of an Absolutely Convergent Series. Okay, and the reference as in Infinite Series 1. My YouTube channel is here. Go YouTube/C. C is for channel /Kumar HCU. That's the name of my channel. You can download the list of videos which are available on my channel from this page, and because it will give you how to study a particular topic in which order. It gives the URL as well as descriptions and also references if necessary. They are all given. It will make your life easier. Okay, right. And it will be periodically updated at least once a month or so. Whenever there is a new playlist is created, for example it's infinite series, there will be about 8 or 10 lectures. So once it's completed, then I will upload the new thing. Okay, right. So let us now start with the thing. So I am given a series an. Okay, call it, I am given a sequence an, the associated infinite series an, right? And remember, for me associated infinite series is nothing other than the partial sums Sn. Very good. Now, okay, suppose sigma is a bijection of n to n. Okay, so let me call it sigma 1 sigma k to be n sub k, right? You understand that? For example, one of the bijection you can think of, the simplest bijection is the transpositions. 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 1, 2n minus 1 goes to 2, and this goes to 2n, and so on, right? Or you can also think of 1 to some n, permute these things, after that everything remains the same. Okay, but these are all sigma 1, sigma n, but these fellows, where do they lie? They all lie in 1 to n. So it's a permutation of 1T n only. So any kind of bijection. Remember, it's a bijection of infinite set. Therefore, okay, but one usually calls it a permutation also. Now let me define a new sequence Bn or Bk to be A suffix sigma n. Right? You understand that? Suppose sigma 1 is 10 and sigma 2 is 3 and sigma 4 is 29 and sigma 5 is 100, then my B1 will be A10 and B2 will be A3, B3 will be A29 and B4, oh, 1, 2, 1, 2, oh, this I didn't do 3, sorry, call it 3, call it this 4. B4 will be 100. You understand this? Okay. So then I have an associated infinite series Bn. Okay. Now the question is, suppose I know this infinite series An is convergent. Does it imply summation Bn is convergent? Okay. Okay. What I said was, okay, Riemann's theorem says the following. What does it say? If a series An is conditionally convergent, that is, summation An is convergent, but summation mod An is divergent. Okay. Then there exists a permutation n to n so that this, okay, for every, let us say alpha in R, and alpha can also be plus infinity, alpha can also be minus infinity, just a symbol, remember that. So that given this, there exists a permutation, so that let us look at A sigma of n. Okay, this will be alpha. If it's conditionally convergent, you can rearrange the series to get any sum. Okay, any real number as a sum, or even you can make it diverge to plus infinity, or you can make it to diverge to minus infinity. Do you follow that? So I cannot expect that for the answer to this in general, no, in view of Riemann's theorem. Okay, that is where the beautiful result comes. What does it say? Let's assume, let An be absolutely convergent. Let sigma from n to n be any bijection. Let Bn equal to A of sigma n, then 1 summation An is, sorry, summation Bn is convergent, and 2 and summation Bn is summation An. Notice that summation An is absolutely convergent, and we have seen any, if summation An is absolutely convergent, then summation An is also convergent. Therefore, if this is S, this is T, then T equal to S. So we know it is convergent, summation Bn is convergent, call the sum to be T, then what we want to claim, this T is nothing other than summation Sn. What does that mean? Again, let us make clear. If Tn's are the partial sums of summation Bn, that is A sigma n, and Sn's are the partial sums of summation An, then what we claim is, the final result says limit this converges and this limit is same as Sn. Okay, Tn converges and limit Tn is limit Sn. Okay, as I keep saying, whenever you think of a sum of infinite series, you should always go to the definition. It is a sequence of partial sum and it should be convergent. The limit is called the sum. Is that clear to all? Okay. Now we want to think of a proof. Right? So let S equal to summation An, that is same as limit Sn. Right? Then what is that I want to prove? So to prove Tn converges to S. Right? And let's not worry about epsilon, etc. If you have been watching my videos on analysis, you will know that I never worry about epsilon, n naught, delta, etc. at present. What I want to estimate, that's all I look at. To prove this, what should I estimate? I should estimate Tn minus S. Right? Now, do I know how to estimate? I do not know. But what do I know how to estimate? Since S equal to limit Sn, I know how to estimate Sn minus S if n is very, very large. Right? Therefore, now you use a curry leaf trick. Okay, therefore, this I can write as mod Tn minus Sm plus Sm minus S. This Sm is the curry leaf. Yeah, so I have to strategically choose this m so that mth partial sum of the series summation an, okay, that is going to be my curry leaf. So this will be by triangular inequality mod Tn minus Sm plus mod Sm minus S. Now you can worry about your epsilon. Suppose you give me an epsilon positive, okay, since Sm converges to S, okay, there exists an m so that for all k greater than or equal to m, mod sk minus s is less than epsilon by 2. In particular, when k equal to m, mod sm minus s is less than epsilon by 2. You understand? Right? So choose, this is given, choose m so that, okay, for all k greater than or equal to m, mod sk minus s is less than epsilon by 2. In particular, mod Sm minus S is less than epsilon by 2. Okay, so second term I done. Now let me look at, so I have to estimate Tn Sm. See, n, still I do not know what n I have to choose. This m is fixed, therefore there is nothing to worry about for me. Right? Now how do I do that? Again, think carefully. What is Tn? Tn is b1, b2 plus b some capital N plus bn. Okay, some n. So I have to choose an n so that for all n greater than or equal to n, I want to say this is less than epsilon by 2. Right? So keep that in mind. But I know this is going to be something like a of r1. This is going to be a of r2. Right? This is going to be a r of n. And this will be a of r of n. Right? This is b1. You understand? So bk will be a of some rk for some k. Right? Rk depends. Remember, it's a bijection. Is that clear? Right. So now do you see that? Okay, you have given me a1. Now what I want to estimate this minus Sm, therefore I have to estimate minus a1 minus a2 minus am. This is what I want to estimate. This will be Tn minus Sm. Right? Now do you see that? Now what I can do is I can choose a capital N so that if I look at b1, b2, b capital N, my a1 occurs somewhere and a2 occurs here, am occurs somewhere. It may occur not in that order. Okay, for example, it may be a10 may occur here, a1 may occur here, a3 may occur here, an minus 1 may occur here, and so on. Am minus 1 may occur here, and okay, so on. You follow that? So this means I will write it loosely, but you have to understand that is choose n such that, okay, my ai occurs in is equal to some bj for 1 less than or equal to j less than or equal to n for 1 less than or equal to I less than or equal to m. That means, okay, this is not set because they may be coincident. Okay, this, okay, this is within quotation mark because some a3 and a7 may be the same. So I am not talking about that. I want the term, seventh term, third term. Okay, that should occur as somewhere as b1 to bn. So the correct way is this. Given any I, okay, there is a j between 1 and n so that ai occurs bj. Do you understand this? Yeah? Just make sure these are the things you should Understand? Right? My A1, A2, AM and so on, but I am just concentrating only on this. Therefore, it has to occur somewhere. Somewhere. This has to occur somewhere. This has to occur somewhere. Right? So choose an end so that all these fellows are found somewhere. Right? Yeah? Okay. Are you following? My A1 may be some BJ. Call it BR1. And A2 may be my BR2. You follow that? So choose R1, R1, Rm. Okay. Choose n to be maximum of these fellows. Alright. Therefore, for each I between 1 and m, my A equal to some Bj where J is between 1 and n. Is that clear? Okay. So pause, review, proceed. Those of you who are confused, let us assume that, for example, my A1, my M is 10, therefore I am looking at A1 to A10. Now I have B1, this may be my A, okay, this may be my A of R1, and B2, A of R2 and so on, right? Therefore my A1 should occur somewhere here, A2 should occur here, okay, make it A equal to M equal to 3 now, okay, it will occur somewhere here, this has to occur somewhere here, this has to occur somewhere here, take that maximum and after that everything occurs. Therefore my Tn minus Sm is nothing other than AK, where K lies in R1, R of 1 to R of n, where n is greater than or equal to capital N, okay, minus 1 to m. Do you follow that? Because Tn will be B1 to Bn, but B1 is AR1, B2 is AR2, Bn is ARn. In that A1, A2, Am occur there, in Sm, A1, A2, Am occur there, they throw them out, right? Only these fellows will be left out. Therefore, I have an estimate for this Tn minus Sm, but that is going to be less than or equal to mod AK, where K is over like this. Are you following? Right. Now comes the crux of the matter. This is a finite sum. Remember that? Right? But if K occurs here, then K is greater than m plus 1. Greater than or equal to m plus 1. Do you understand that? Therefore, this is a finite sum of terms AK, where K is greater than or equal to m plus 1. Okay, but it's a finite number of terms. Okay, now let's look at AK. K is greater than or equal to m plus 1. This is the tail of the series. Right? This is a modulus. Right? Now what do I know about this? Since summation AK K greater than or equal to 1 is convergent, that is absolutely convergent, therefore there for epsilon by 2 there exists an m so that m plus 1 to infinity of mod AK is less than epsilon by 2. Right? Are you following? But remember, this m is not at your control. You already have chosen that k m earlier. So what do I do now? Now go back and do something. What do I do? Let's go back. So I choose m so that this happens, and summation mod AK K greater than or equal to m plus 1 is less than epsilon by 2. So you follow that? So here, okay, choose m so that 1 this happen, and 2 summation mod AK K greater than or equal to m plus 1 is less than epsilon by 2. For example, for this there will be m1, and for this there will be an m2. Take m to be maximum m1 and m2, then both these conditions are simultaneously satisfied. These are all the standard analysis, right? Okay. Are you following? Therefore, what do I have? Therefore, I have mod Tn minus Sm is less than or equal to k greater than or equal to m plus 1 of mod a k. Again remember, I am using the definition of sum of an infinite series of non-negative terms. This is a non-negative term, therefore this is going to be what? This is going to be supremum of mod a k greater than or equal to m plus 1 to some n, as n varies over n plus 1. That's the infinite series. And this is just a finite number of terms, so each one of them will be less than or equal to this sum. Are you following? But that is less than epsilon by 2. Therefore, that's less than epsilon by 2. So, what do you think I have proved? So, I have proved that, okay, given epsilon, okay, choose m such that mod sm minus s, okay, sk minus s is less than epsilon by 2 for all k greater than or equal to m, and 2 summation mod a k greater than or equal to m plus 1 is less than epsilon by 2. Next, what do I do? Choose n so that for all I 1 less than or equal to I less than or equal to m, there exists a j in 1 to n so that my ai equal to bj, right? Therefore, what will happen if I take tn minus sm, okay, this will be b1 plus bn minus a1 minus am, but they will go with something else, right? So therefore this will be some AR, sum of AR, where R is greater than or equal to m plus 1. And it's a finite sum, not all greater than or equal to m plus 1, right? Therefore for any n greater than or equal to capital N, mod Tn minus Sm is less than or equal to mod Ak, where k is greater than or equal to m plus 1, which is less than epsilon by 2. Therefore mod Tn for n greater than or equal to capital N, mod Tn minus S, remember this Sm is a curry leaf. So that's it, proof is over. Okay, pause, review, proceed. Okay, this is a very beautiful proof, as I said. This is a very beautiful proof. Go through it. I took lot of pains to explain that idea. Again, rewind, replay, make sure that you understand. Try to think along with me. As I keep saying, do not worry about remembering or recalling the proof. Okay, good. Next, what we want to do. So this is the second part of the lecture. Second part of the lecture is what I will call summation by parts. Okay. See, so far if you notice, we always looked at a series of non-negative terms, and then we talked about absolutely convergent thing, and the substantial results were about non-negative terms, and we had a comparison test, ratio test, root test, and if it is absolutely convergent, the series is absolutely convergent, then it is convergent, and any kind of rearrangement also it will converge, and it will converge to the same sum. These are all beautiful results. But unfortunately, in certain parts of analysis, you don't get only absolutely convergent series. Okay, the most important case is the so-called Fourier series. Okay, there you will have something terms of the kind a and cos nx and plus b and sin nx, etc. Will be half of a naught or something. Let's not worry about this kind of objects will be there. Okay, so now you can see these are all highly oscillating. Okay, so one has to learn to do that. The trick is, okay, notice that this is a product of two things, one this and another thing. Okay, so this trick is due to Abel. Okay, this summation by parts is this analogous to integration by parts. Okay, so let me recall the integration by parts. Suppose f and g are functions from a, b to r, and let's assume continuously differentiable. Yeah, therefore that is f dash g dash are continuous, exist and they are continuous. Then what does it say? F dg between a and b, which also one writes as f g dash between a and b. This is equal to, look at f g at ab minus interval f dash d. Oh, f dg, right? F dg, therefore f, okay, g df, that is f g at b minus f g at a minus interval g d g df, right? F g dash equal to f g within the limits minus interval f dash g. Is that clear? Yeah. This is the way I learn, but nowadays because of American textbooks, the integration by parts formula looks a little weird for me. But anyway, this is very easy. Okay, right. So now let us look at this. Suppose I have two sequences an and bn, and I look at an times bn. I want to talk about the convergence of this. I want to discuss the convergence of this series, right? So let us look at the partial sum a1 b1 plus an bn. Okay, this, the trick is I want to write it as a sum. Let us look at, okay, I have this associated infinity series summation an, associated infinity series bn. Instead of my Sn, I will call it an, the nth partial sum. And similarly bn, the nth partial sum. What does this stand for? An equal to a1 plus an. This is what we used to call Sn, right? Okay, the reason is you will know this is a very standard thing in Abel summation formula. That's why I am using this. Therefore, I can write this as a1. Let me also look at a0. Okay, let a0 be this. Therefore, I can write this as a1 minus a0 into b1 plus next will be a2. That will be a2 minus a1, because a2 will be a1 plus a2 minus small a1. Therefore, I get a2 into b2 plus last one will be an minus 1 bn. Do you understand this? Yeah. So this finite difference, one usually calls it delta ak, is a ak minus 1. Do you remember when you talked about differentiation, you will write as summation f, integrally summation f of, okay, delta xi or some such thing, f of x into delta xi, some such thing. Okay, I do not know, because people only work with now, algorithm. Okay, you may not realize, you might have seen such a thing. Therefore, this is why this is something like delta a1 b1 plus delta a2 b2 plus delta an bn. This is like your derivative, a dash b, a dash b, a dash b. This is integral. Okay, this is a finite sum that's considered as an integral. Are you following? Yeah. Okay, that is why this. Therefore, what should happen then? Let's look at the integration by parts formula. It said something like this: integral f dash g is f g minus between a and b, of course, minus integral f g dash, right? Therefore, f dash is my delta a. Therefore, it should be a into g is b. But remember, it should be at what and what? It is 1 and n, right? At start with 0, therefore it's 0 and n. Okay, so minus the other sum should come as f, that is going to be, what is your f? F is going to be your a into g dash will be db. Are you following? F dash is this, therefore f, okay, into dg, a into delta b. Are you following? Don't worry if you don't realize, nothing is lost. Okay, but let's just go to what we did. So I have a1 minus a0 into b1 plus an minus 1 into bn. This is my summation ak bk k equal to 1 to n. Okay, now collect these things. This is going to be ak bk k equal to 1 to n minus ak minus 1 bk k equal to 1 to n. Right? But remember, when k equal to 1, ak minus 1 is a0, which is 0. Right? Therefore, this actually starts from a0 b1 plus an minus 1 bn. Right? So I want to change it into, because remember, what do I want? I want it a completely. Here it is. When I try to bring them down, it will be ak minus 1. I don't want. So what I want is the same k. So ak bk k equal to 1 to n plus, sorry, minus. Okay. Now change k equal to 1 to n, k minus 1. So I look at only this one, a k and bk plus 1. Are you following? So I will have a1, b2, I'll have, and so on. But then when k equal to n, I had an extra term, namely plus an bn plus 1. That is not accounted for. Are you following? Pause, review, proceed. Yeah. So this I can rewrite now. K equal to 1 to n, ak into bk minus bk plus 1 plus an bn plus 1. Just make sure I'm writing everything correctly. Sometime, in my hurry to explain, I may forget some signs, etc. Just make sure that I get it correct. Okay. If I'm explaining on the board, I have a big board so that I know what I'm writing, so there will not be any mistake. Here, as you can see, it's hidden, so I may make some mistakes. Okay. So this is exactly how that form I wanted, right? So remember, my delta b, if I want to write, that should be something like bk minus 1. Therefore, this I should write as k equal to 1 to n with a minus ak bk plus 1 minus bk plus an bn plus 1. So you can see it's exactly that form, minus a into delta b. Do you see that? Yeah, right. You keep writing on a notebook and then you can see it precisely. So this is called the summation by parts formula. So Abel's formula, what is this? Summation ak bk k equal to 1 to n is summation minus ak into bk plus 1 minus bk plus an bn plus 1. Okay, right. Now what do I do with this formula? Okay, that's what we want to look at. So I look at that. Our original aim is to discuss the convergence of this fellow, right? So, but that is written as this is a series 1 to n. Okay, I want to discuss the convergence of this infinite series and the convergence of sequence of numbers. Okay, this is an bn plus 1. This is a sequence of numbers. This is a partial sum of a series, namely ak bk plus 1 minus bk, but for sign. This is a sequence. But this is 1 to infinity. If you write, this is a series. You understand? The convergence of this is going to be the convergence of this and this. I am breaking into two parts. So if I make sure this converges, and if I make sure this infinite series converges, then I know this series converges and I have a sum. Do you follow that? Okay, I am arriving at the result. You see that? I am not saying that take this, live with it. Now let us say I want an bn plus 1 should converge. Okay, so what kind of thing I can do? There are two ways of doing. One, assume bn itself converges and an itself converges. An converges is the same as saying this is convergent. The infinite series is convergent, right? Okay, But look at this. This is bk plus 1 minus bk. If you remember, have you seen something similar? When we looked at the series 1 by n into n plus 1, okay, this is what we call telescopic. This we wrote as n minus 1 by n plus 1. Therefore, when I take partial sums, okay, like a telescope, things cancel, so that I will be left with very simple formula. You see that? So that suggests maybe I should look for some kind of telescopic thing here. Okay, I should look for a telescopic effect. Right? So how can I make sure it's telescoping effect? Remember, if I assume an is convergent, even if an is bounded, let us say an, okay, modulus an is less than or equal to m for all n. So if it is convergent, of course it will be bounded also, right? Then let us look at this series. AK bk plus 1 minus bk, that I can write as, okay, or bk minus bk plus 1. It does not matter, okay, 1 to n. Okay, this in modulus will be less than or equal to mod ak into mod bk minus bk plus 1, but that will be less than or equal to m into mod bk minus bk plus 1, k equal to 1 to n. Are you following? Now this should be convergent, right? So what I can ask for a telescopic effect. Therefore, if I assume my bn decrease, then bk minus bk plus 1 will be positive. Therefore, mod bk minus bk plus 1 will be bk minus bk plus 1. Therefore, this will be b1 minus b2 plus b2 minus b3 and so on, minus bn minus bn plus 1. So b1 minus bn plus 1. So this will be less than or equal to m into b1 minus bn plus 1 with the, are you following? Yeah, right. So if it is decreasing, I can have a telescopic effect. Therefore, when I am saying it's a decreases, then you can see what are the conditions I can do. There are two ways. One condition is assume an converges, that means summation an, this infinite series convergent, and bk decreases, right? And the second, these are sufficient conditions. Second condition, another, this is a separate, okay, second sufficient condition. This is, let us assume ans are bounded and bn decreases to 0. Okay. Now notice that if ans are bounded, bn decreases, the telescopic effect still takes place. But when it comes to, now let's look at, now ans bn plus 1, this is bounded, but this sequence decreases to 0. Therefore, this sequence goes to 0. Therefore, it still converges. Have you understood this? We discovered the result. I am not saying. Okay. So we have proved two results. One is called Abel and another one is called Dirichlet. Okay. The convergence of this series is what I am looking at. Okay. So if the series an is convergent and bn decreases, and Dirichlet theorem says this an partial sums is bounded and bn decreases to 0. Okay, then the summation a and bn is convergent. So unfortunately, because of time constraint and also it involves a lot of trigonometric identity, as I said, okay, an cos nx, suppose an, okay, goes to 0, sorry, decreases to 0, right? Then you can show that cos nx kx k equal to 1 to n, etc. for x not equal to a multiple of 2 pi, then you know this will be bounded. Okay, then you get convergence of this series. Okay, refer to my book. Okay, this is one of the Dirichlet test for Fourier series. So I hope you enjoyed the way I arrived at Dirichlet's test as well as Abel's test from Abel's summation formula. Okay, right? Summation AK BK k equal to 1 to n. That partial sum we wrote it as a partial sum summation capital AK into BK minus BK plus 1, but for sign, and plus AN into BN plus 1. So this sequence of AN BN plus 1, I have to say it converges, and this sequence of partial summation capital AK into BK minus BK plus 1 converges. If I make sure these two things happen, the original series summation AK and BN converges. For that, what kind of condition I can impose upon either the series summation AN or the partial sums capital ANs or on this sequence BN, right? In both the cases, it decreases as a necessary condition because I want a telescopic sum. And in one, if I assume only ANs are bounded, I wanted BN to decrease to 0. Therefore, AN into BN plus 1 will go to 0. Whereas in the other, if ANs are convergent, then AN converges, BN decreases, okay, and sorry, decreases to unconvergent, then A and BN plus 1 will be convergent. So I should have said that convergent. I didn't say that, but you can assume that. So I hope you enjoyed the lecture. Stay tuned. We'll come up with the next lecture soon.